Hello everyone, Miranda Pickett here. This is my Advanced Concepts presentation for Module 2, and today we're going to be talking about the Michaelis-Menten equation. So to kick things off, we'll start off with reaction 1, and reaction 1 is E plus S, and then we have our double arrows here equal to ES. So a couple things to note here is that E equals enzyme, S equals substrate, and ES equals our enzyme substrate complex. One other thing to note here is that we do have a double arrow here, and this is meaning that the reaction can go both ways, meaning that we can either break down the enzyme substrate complex or we can move on to create a product. Which brings us to reaction 2. Reaction 2 is ES, and then we have a single arrow here, something to note, EP. So basically what we're saying here is that we're going to be breaking down the enzyme substrate complex so that we can get a product. We have a one direction arrow here, which is something to note, which means that the direction can only go one way. The reaction can only go one way. And it also basically means that there's just not enough products here to be noticeable. So then we're going to assign some variables. The first variable we're going to assign is K1. So K1 is going to be assigned to our forward part of reaction 1, so it's going to go here. Second variable we can assign is K-1. K-1 is going to go on the backwards reaction of reaction 1. Lastly, we have K2, and this is going to go in our only direction of reaction in reaction 2, which is our forward reaction. We also are going to have to verify that the mechanism is valid, and in order to do this, we're going to add reactions 1 and reaction 2, and we're going to come out with S to P, which basically means that the substrate's moving to product. So we can, once we've established all of these things, we can start to solve. So we're going to solve using the steady state approximation, which just means that the enzyme substrate complex is going to equal the sum of all the reactions that are working to decrease its concentration. Or you could say that K1 minus K-1 minus K2 is equal to 0. And basically K1 here creates the enzyme complex, while K-1 and K2 consume it. Now that we've decided all of these things, we can now write out the instantaneous rate of change, and that's going to look like something like this. Apparently I can't talk tonight. D times ES divided by dt equals K1 times enzyme times substrate minus K-1 times enzyme substrate complex. And let me see if I can move over here just a little bit. Minus K2 times enzyme substrate complex. And all of this is going to be equal to 0. What this basically, this whole thing right here means is that the reaction rate is only going to depend on the concentration of the reactants that are involved in the reaction. The only problem is that it's going to be difficult to calculate the value of the enzyme that hasn't been bound. So we got to fix this problem somehow. So in order to fix this problem, we're going to say that the total enzyme, which is what this right here means, is equal to the enzyme plus the enzyme substrate complex. So as I said, this right here is the enzyme total, this is the enzyme, and then this is the enzyme substrate complex. Or you could think about it as the enzyme, the total enzyme, the unbounded enzyme, and the bound enzyme. Now, in order to continue with our problem, we have to subtract ES from both sides, and then we're going to solve for E. And once we do that, we're going to end up with enzyme, or the unbounded enzyme, is equal to the total enzyme minus the bound enzyme. From here, we can substitute the total enzyme minus the bound enzyme into the previous equation that we had for E, and we're going to end up with, D times ES divided by dt, which also, as we know, equals 0, equals K1 times our enzyme total minus our ES. Again, I'm going to have to move over here. Times S minus K negative 1 times ES again minus K2 times our ES again. Then we have to distribute our K1 plus S in the first term. And that's going to leave us with 0 equals K1 times our total enzyme times S minus K1 times our ES again times S. Sorry, I'm trying to get this pens to work. It's my first time using this program. Where are we at? We got the K1 minus K1 times our ES times S minus K negative 1 times ES. And then to finish it out, minus our K2 times our ES again. Alright, now that we've done that, we can try to start solving for the concentration of ES. So that means that we're going to have to move all the terms of ES to one side of the equation. And once we do that, we will get ES, which will be our, sorry there, guess I pressed too hard, ES times K1 times S plus K negative 1 plus K2, which will equal K1 times our total enzyme times S. Again, we're going to continue to isolate the ES, so in order to do that, we're going to say ES is equal to K1 times our total enzyme times S over K1 times S plus K negative 1 plus K2. And in order to continue that even further, we're going to multiply that whole section right here that we just did by 1 over K1. And once we do that, we will get ES is equal to our total enzyme times S over S plus K negative 1 plus K2 over K1. And that's going to be important to remember for our next step. because now we have to determine the instantaneous rate of the change for the product. And that's going to be equal to d times p over dt equals K2 times ES. And remember I said that's going to be important because now we can plug in that equation that we did. Let me try to circle it in another color right here into our new problem, which is down here. Alright, so once we do all that, we're basically going to get velocity. And velocity, or V, V equals velocity, and velocity is basically just the reaction rate. And it's going to equal d times p over dt, which also will end up equaling kcat times our total enzyme times our substrate over our substrate plus our Km. And our kcat is basically just K2 made over. It also represents the turnover number, which is basically the max number of molecules of substrate that an enzyme can work in its equation or convert to its product per second. All right, and then we got to talk about Vmax. So the Vmax is just this part right here. So it's kcat times our total enzyme. And then when we're talking about Km here, Km is essentially half of Vmax. That's how I like to remember it. Km stands for the Michaelis constant, and it's actually equal to K negative 1 plus K2 divided by K1. Or you could write it alternatively as Vmax times your substrate divided by 2 of your substrates. And essentially what will happen here is that the S's, the substrates, will cancel out, and you'll be left with Vmax over 2. Sorry about that again. You'll be left with Vmax over 2, which is also equal to our Vmax half. And something else special to note about Km is that with Km, if our Km is low, then our affinity is going to be high. And if our Km is high, then our affinity is going to be low. I think that just about covers the Michaelis-Menten equation. I promise I have better handwriting than this, but this is on my computer, so this was the best way that I could figure to do it. Like I said, it all starts here, and we can go all the way down to here. This is the important part. Anyways, I hope that wasn't too confusing. If you have any questions, feel free to ask, and I'll do my best to answer. Thank you for watching, and I hope you all have a great night.